So we are going to be talking about simple harmonic motion. I'm just going to put a bunch of definition stuff on the board right now, mostly just copy it down right now. Okay. Simple harmonic motion henceforth known as SHM, so that I can shortcut it as well can you. You can feel free to say SHM from this point to refer to this. Is an oscillation caused by a restoring force. Now, restoring force might look like a generic word, but it is a vocab word. It is a very specific set of qualities on a force. A restoring force has two qualities. Number one, it points towards equilibrium at all times. Okay? And number two, the amount of, is that the word I want? Yeah. Don't like it. The amount of force is proportional to its displacement from equilibrium. All right, bunch of fancy words, so I am going to do my best to try to break this down a little bit easier. Oscillation is anything that repeats itself. So like going around on a merry-go-round, that is circular motion. That is a type of oscillation. That is not simple harmonic, although just as kind of a point of interest, it will be used later because it is very akin to simple harmonic in some of its math. So we'll drop that right now. So let's talk about a couple of oscillations that are not simple harmonic and one that is, so that you can look at, okay, great, what the crap does all of this particular stuff mean? Okay, let's start relatively simple. Sorry for people online, I'll describe what I'm doing. All I'm going to do right over here is I'm going to walk back and forth across the front of the classroom. Okay, we're going to say that this post in the middle of the desk is going to be my equilibrium point, or just the middle of the path. I walk back and forth like this. Cool. Am I oscillating? Yes. Am I repeating myself?
Yes.
Yes, I am oscillating. Okay, so the question is it simple harmonic? So you look at both qualities. Number one, when am I actually putting a force out in my muscles to change? Okay, well there's kind of a couple of it. I want to get really pedantic here. Okay, one, when I'm accelerating. Two, I'm pivoting my foot. But also technically there would be some in the middle, right? What would the force be in the middle as I'm walking through here? Right, it would be equal to friction. So in other words, I'm looking for, it would be just constant straight through the middle. Okay, so let's start with the easy stuff. Number one, does that force of my muscles always point towards this location?
No.
Heck no, right? As a matter of fact, my force is going this way, and the moment I cross by here, nothing happens. It goes this way until over here I try to stop and it'll point back that way, and then having to accelerate it would point back that way. But as soon as I cross over, it does not always point back towards equilibrium, right? Number two, what does the word proportional mean?
The same.
No.
No, like if this is 1, then this is 3, and then if this is 2, this is 6.
Okay,
I don't know
I like the
this
numbers, it's fine. Number one, they increase together. Let me tell you this, if you don't already have this in your head, this is a really good SAT test question. Proportional is the same as a relationship that we have used all freaking year long. Proportional is a fancy $10 word for what relationship that we have used all year long? No. What are the four relationships? If I say relationships, what are the four relationships that we've used all year long? Come on. Mathematical relationships we've used all year long. Names of mathematical equations. Yes. Sure, if you as you need. Come on.
Can you give us one example?
Okay. There are things that you should blame a teacher for being too hard. This ain't it.
No, I just like don't understand. Like,
Mathematical relationships means a relationship between mathematical quantities. As one changes, the other changes, and we give names to these. There are 4 that we did all linear, parabolic, hyperbolic, and square root are the names of the mathematical relationships. Do not even with language on this. I get irritated at students, specifically AP students, who will be like, well, I think the words are written wrong. I had a conniption fit with Physics 2 a few chapters back. Like, the book is explaining this wrong. Oh, child, you mean the 3 individuals who are the greatest in your field who wrote this together collaboratively along with a group of individuals to find the most correct way of saying this, that goes revisions every single year to make it better and more organized, is not well written enough for you, a brand new novice to the subject? Out of the 2 of you, perhaps there is one that we should hold more responsible. And perhaps you not holding yourself responsible might be a reason for you not making progress in the field. Sorry. That was at Physics 2. Totally, absolutely nothing that any of you in here have thought ever. I apologize for even saying it to you. All right, so point being, yeah, what is the mathematical word that goes with proportional? There were 4 of them. Linear, correct. Proportional is the... There are multiple people talking, and you didn't talk particularly loud. Humor. I apologize for not hearing it. I'm not perfect. Okay, linear. Yes, that means linear, which means what Elias said at the very beginning, which also should include you in. A linear means if one goes up and doubles, the other one is going to double. Exactly right. If you can't see that, here it is. Okay, if I have y and x, boom, here is an x. Here is a y. We'll call them y1 and y2. If I double x1, what does y2 do? Double. And triple and triple and quadruple and quadruple. So, back here, what does it mean is happening between these 2 right here? Yeah, another way to say that too is how big should force be at equilibrium? Force at equilibrium should be 0, or at least its net force should be. We're going to look at a relationship now, or a thing for this spring system that is not quite perfect, but it has the best case of like helping you understand it to begin with. It's this. We're going to say that the spring right now is up in space, okay, and like attached to a wall. Okay, and the main reason we're doing that is so that I can ignore gravity right now, which is obviously what you could do in space. It would work completely fine, right? What is this point where the spring would naturally be sitting? This is a review from previous, what's it? Equilibrium, correct? And equilibrium is a fancy $10 word for what? Newton's first law, or sum of forces is equal to 0 at that point. And in this particular case, if it's up in space and it's not stretched, there would be no forces acting on it whatsoever. So this is simple harmonic motion. How do we know? Does it qualify both things? Well, let's check the easy one first. Number 1, if I take this mass and pull it to the right, what's the spring going to do? Pull it to the left, which is back towards equilibrium. The moment it goes back to the left and crosses by the equilibrium point and goes over here to the left side, which way is the force going to point? Back to the right. So, does the spring satisfy point 1? Cool beans. Next, to help us with the next one, as a matter of fact, to help us with number 1, remind me real quick, what is the full equation for the spring force? You just used this in the lab. Okay, almost. And I don't blame you. Just a reminder, this is technically the absolute value on that. If we go back to the straight up legit one, and I'll explain to you why you should and shouldn't, what's missing? The negative in front of this right here. Okay, now the reason why we usually ignore that negative is what just happened a moment ago. If I pull this right, did anybody need the negative to say that it's going left? No, so it's completely fine to ignore it. The only reason I add it back in is what you can see is it mathematically in the equation satisfy number 1. Because the reason that negative is there is that if this is positive, you want this to be, and if this is negative, you want that to be. So literally, as you look at that equation, 100% a short answer on a test would be, show me in this equation where both parts of simple harmonic are satisfied, and you would go, hey, that negative satisfies condition 1, that the force always has to be pointed back towards equilibrium. Yes? And I bring that all up because, like I said, that's the easier one, but the harder one, which actually isn't that hard at all, is the amount of force proportional to the displacement from equilibrium. We already just said a second ago, proportional means what relationship? Linear. Okay. Is the force linearly related to delta x based on that equation? Well, is that to the first power? Yes. Is that to the first power?
Yes.
Yes. Meaning if you were to graph the force versus delta x, it would make this shape, and see previous conversation, for a certain x, there's a certain force 1. And if you were to double that particular guy right here, what would happen to force of spring? It would double. Okay, going back to my original crappy example, and then we'll go somewhere in between the two. As I walk at a like this right here, we already said the first one isn't satisfied. Is the second one satisfied? Is the distance from equilibrium changing how much force I'm putting out? Yeah, absolutely not. As a matter of fact, before I accelerate, especially if I make the distance, the amplitude relatively big, you can see most of the time the force is constant. It's not changing in any particular way, shape, or form. But with a spring, where is a spring pulling the strongest? When is a spring pulling the most? When it's the furthest away. And what happens to that force as the displacement gets less and less and less? And actually, if you looked at that displacement, as the displacement cuts in half, the force will cut in half, and you get all of this relationship right here that you're seeing. Now, of course, you can see that the annoying part of the vertical system, and why I kind of ignored it up here, is that we have to add gravity. I will do that here in a few moments to talk a little bit more about that. Let me remind myself real quick. Yeah, okay, we're good. I have 3 things left to cover, and then I'm going to try to be done as quickly as possible here. Let's talk about that vertical one first. Okay, now this conversation, I'll tell you, is a start of a conversation. When a conversation is deep and difficult, it is good to kind of drop this in your head and start to think about it, but understand that it's going to take time for your brain to develop these particular thoughts. That's why it's so important to start homework and all that sort of thing early in a chapter and not later, because your brain cannot learn stuff beyond its own natural speed. So let's talk about the vertical system, knowing full well that there's going to add, we'll add some more details a little bit later. Let's go back to yellow. Come on. There we go. All right. So this is your lab. Okay. What's the force diagram as this is sitting here at equilibrium? Gravity down and spring up. Cool. All right, humor me real quick. Take 30 seconds. Shouldn't be that hard. Draw a force diagram of that mass when it is both below and above the equilibrium. And for sake of argument, I will make the distance below and the distance above the same amount. If that matters to you, cool. And if it doesn't matter to you, hopefully it eventually will. Okay, so there's a distance down here. Draw the force diagram of this guy down here, and draw the force diagram of it up top.
That's yes, that's probably bouncing away. Or my pencil working. It's not working.
My pencil ain't working.
Can you not be mean? I clearly am tired.
All right, underneath. What should be on this underneath? Gravity. Okay, now let's talk about this. What should change or shouldn't change? How should this gravity here compare to the gravity under here?
The same.
Should be exactly the same, correct. So force of gravity is not changing size just because of where it's at, yes?
Yes.
Cool. What other piece then is that force diagram? Force of spring should be bigger, correct. I'm going to try to draw a comparison here for a conversation we'll have in just a minute. Okay, yeah, it should be bigger. So the whole thing up here, even with this line, that's all force spring right there. All right, now what about above? Once again, with force of gravity, what's the case?
Yes.
Same. Which way should force spring go? How should force spring compare to force gravity? Smaller. Okay, but that's where it gets a little tricky. because the displacement down here is equal to the displacement up there, and that displacement changes how much force spring there is, that means however much extra is here is the amount that should be missing from the spring on top. Does that make sense? Okay. So, this is then all to say, does gravity, in case anybody I didn't get to you during the lab yesterday, does gravity actually affect the mass spring system? Well, it feels like it should, but you are right. The answer is no. So let's talk about what would change and why things do or don't change. So right here, actually, let's not do that one. I got this lined up on purpose for a reason. Checked it earlier, check it over here. That's 1 second. That is a period of 1 second. Let's say I took this exact same setup to the moon. Okay? What would change if I was on the moon?
Period would be over.
Start here, just right here. Just sitting. There's no period right now, or there's not supposed to be.
It wouldn't
So,
be stretched as far.
Would not be stretched as far, so the equilibrium point would be at a different location. Yes? But if I stretch this 5 centimeters, it gets a certain amount more of force because of the spring, right? Even if it starts up here on the moon, and I stretch it 5 centimeters, does that difference in the spring still exactly the same on the moon as it is here?
Yes.
Yes. So, would the period be any different on the moon because of gravity? The answer is no. The best way to see that, and again, just a gentle reminder, this is a hard conversation. If you're following it, awesome. If you are not, even if you are following it, I would revisit it. Here's probably the best way to think about it. If I could sort of ignore gravity, or kind of like cancel gravity out, these two would cancel, right? Such that your net would be 0 at equilibrium. Down here, this would cancel with this. This extra bit right here is a direct result of force of spring. Yes? Finally, the hardest part. Once again, I'm going to do kind of the same thing. I'm going to cancel out the force of spring with force of gravity. Now, you would make the argument that gravity up here is what causes the acceleration. Yes? Except it's only causing that acceleration because this amount is missing, which is because of force spring. However much this is missing up here is how much extra is right there, and we already said, is this amount missing equal to this? So is this force up equal to this force down and both caused by force of spring? Yes. So spring is the thing that actually holds it back and forth. Gravity doesn't actually in this particular case. Again, we'll talk more about that later. How are we feeling? Fist to 5. Love you guys to death. I would put lower numbers on that just based on my own hearing of my own explanation. All right, moving on. Let's talk about a pendulum real quick. We have not talked about, I know what I didn't do earlier. I meant to do this. Okay. So I did a very obvious not simple harmonic motion by walking back and forth.
Yeah.
Okay. We use the mass of spring. Say that is definitely simple harmonic motion. Okay. Discuss quickly in your group. I'll give you about 30 seconds to a minute. If I take this in my hand, I put a pen, you can do it yourself, and flick it back and forth like this. Okay, is this an oscillation?
Yes.
Yes. Is it simple harmonic? Let's assume this was a test short answer question where I asked you, is this simple harmonic? And you said no. Now back it up. Discuss quickly to your why is this not, I agree with you, why is this not simple harmonic?
Your fingers are only this far away from the board.
Yes.
I actually don't know. I made that up.
Yeah.
Because like this is little and this is big.
I mean, it's not
I heard displacement.
Because it doesn't point to
Did you know the word pendulum does not have a G in it?
Yes, Haley, I did.
I did.
I didn't know that.
I very much did.
Because I thought it was pendulum.
To be fair, for whatever reason, I have my own flaws in spelling certain words in physics. my big flaw, I don't know if you guys noticed this, I always swap the O and the U in buoyancy. I totally mess it up all the time. It's supposed to be-
Really? I got
You was
four.
supposed to be first.
I got
You was supposed to be first.
Yeah, I can't spell buoyancy, I can't spell guard, and I can't spell the verb.
I just can't spell.
Anyway, all right, let's talk about it. Why is this flicking your pencil back and forth in your hands not simple harmonic? It doesn't actually satisfy either condition. Let's talk about both of them.
It doesn't have
Yeah, for starters, when you get to this particular spot, you're probably close. But like right here, does this finger pushing back automatically take over as it's flying past? No, it probably doesn't actually take over until it's towards the edge.
Yeah.
And that's it's kind of a short answer thing, but yes, definitely doesn't always point back towards equilibrium. And probably the more obvious piece of this, the most obvious one, is the second condition. Why is the second condition not met? I am not making sure that my fingers are pushing then a small, medium, large, proportionally all the way out on displacement. Quite frankly, I'm probably doing what I did over there. I'm just applying a steady, constant amount of force the moment I want to push it, turn it back, and go back the opposite way. Yeah, so it's definitely not going to be linearly proportional either. That being said, this is going to matter for what we're talking about right here. If we look at kind of a scale of oscillations on a not simple harmonic to simple harmonic, what we have right now is like this guy is an oscillation, and certainly more simple harmonic than just walking down the hallway. Let's call this, just for sake of an arbitrary number, 10% simple harmonic motion. Okay, what is this? Well, it's not simple harmonic motion, but it's kind of harder to spot the differences in this than that one. It's certainly closer. So again, arbitrarily, no specific numbers here, do not write these down. This is like, I don't know, 70% simple harmonic motion. The mass spring system, I would argue by itself, is 100%. But what thing have we gone back to ignoring which would directly fight against friction? Is friction ever going to allow us to push back towards equilibrium perfectly when you're supposed to? No, because it always goes the opposite of velocity, which, by the way, friction is the reason why this will eventually slow down to an amplitude of 0. If there was no air friction in here, there is still friction inside this, so if we put this out in the middle of space, in this particular, assuming there was gravity, obviously, and it was going back and forth, it would last ridiculously longer. Okay, like it would eventually stop. The main reason it would eventually stop is because, like I said, internal friction inside the spring itself, but it would take a lot longer. Let's talk a pendulum now. There's probably a reason I connected all that, or I'm just making this up. Let's find out. What's the force diagram on the pendulum?
Gravity straight down and then tension up into the right.
Cool. So, what force is it? What force is it that causes the restoring force here? A little more specific, and I'm with you. Tension in the X. Okay, so let's check. Does tension in the X qualify both of the two qualifications to be simple harmonic motion? Equilibrium would be right about here. Yes? Okay. This is currently left of the equilibrium point. Is tension in the X pointing towards the equilibrium? Cool. As the pendulum comes by and swings by past the equilibrium point, the moment it swings by, does it automatically tension in the X switch direction so that it's still pointing towards equilibrium? Yes. So in other words, you're on the left side, force points right. You're on the right side, force points left. Boom, we've knocked out position number 1. So cool beans, let's go back here, let's go back here, let's go back here, and oh, darn it. Didn't think it was that far back. Cool, we've knocked out number 1. Number 2, here's a problem. I'm going to require on some pre-calc conversations here, but my apologies. What is the equation? What did we use the other day for displacement from equilibrium? What did you measure to get displacement? You didn't measure just distance like you did with, but you measured angle. And my guess is you measured this angle right here, yes?
Oh no, we're doing triangles.
Yeah.
Yes. Okay, so you measure that angle right there. And on my triangle over here, if you don't recognize, that's where that angle goes. Yes? So if I was going to find tension in the X, and pretend for a second I know what tension is, okay? Tension in the X, what relationship with tension itself? Trig. Just tension in the X. Here's tension. There's the angle. Oh, careful. Look at where the angle is.
Sine.
You want this piece over here, yes? So You need sine theta. Okay. So earlier I used what's known as Hooke's law. If you didn't know that, that's what that's called. That's that negative k delta x to show that it was a linear relationship between force and delta x. Yes? Okay. What did you tell me what we're using for displacement? You use theta. Okay. And what's the force, the starting force? Tension in the x. Is there a linear relationship between the two?
Yeah.
Oh, come on, pre-calc people. Let me try this again.
Is it no?
Well, obviously, but that's not the point that you know the answer if you know idea. Again, let's be really clear because somehow I think we've missed this all year long. If you know the answer and don't know the reason why, you're more screwed than if you didn't know the answer.
I was really
Okay? Because the problem with some of you guys is you get the answer and you stop, which is not the point. So if you get the answer and stop, you screwed, kid. All right, moving on.
What did you write on here?
What's that look like?
Is it because they don't know the same number?
It looks like no sanction. No.
This, yes? Cool. That is y versus theta. Actually, let's just make this theta instead. Now, for our purpose in here, okay, what is the angle? Well, the angle, okay, is this guy right here.
Yeah.
So are you probably going all the way out to 90, 180, 270, 360? No, my guess is at most you would probably swing it all the way out here, in which case the angle would be 90. So we don't really need all of this. As a matter of fact, let me go back here to a relationship you made earlier. Okay, you just need this. Yes? Because tension in the x is equal to T sine theta. This is tension in the x, where this is theta. So is it going to straight up be simple harmonic?
No.
Which feels dumb that I would present all of this to you and then go, that's not simple harmonic, so let's talk about this. Let's pretend for a second. Let's just pretend. What would it need to be so that it was simple harmonic?
Oh, no.
Well, how would you change the equation?
Linear regression.
No, not there yet.
Probably like cosine.
Nope.
I don't know.
You need it to be proportional.
Tension in the.
Tension in the x is equal to tension times, what's that?
Oh no.
Theta. Now they're to the first power. And if I was to graph this guy, what would this look like?
Linear.
So if I graphed it on top of each other, it would look like this. So, it is this, it's not this. But if you look up over here, is there a certain region of angles where it's not simple harmonic, but it's stupid close? Like, just pictorially, hopefully you can see that basically in that region right there, it's not simple harmonic, but it's definitely not on the scale of things. It's certainly not like 10%. It's definitely not even 70%. Within this range right here, you would even argue that that's stupid close. So what is that angle? Well, number one, I'm going to show you the math of this real quick. I apologize. Please, all of you guys, get out your calculators real quick. That's a good thing to know anyway. Okay. Let's look at stuff, and we got to do radians, so here we go. Let's look at for 3 degrees. What's the angle in radians, and what's the sine of the angle? Do you remember how to convert degrees to radians? Let's talk about it real quick. All right. Yes, you're not wrong, but also you're wrong because, again, it's that thing where you guys know the answer, but not the reason why. All right, so if you remember, what I told you was this. What I liked was 57.3 degrees is 1 radian, okay? I like it because I've got a 1, I've got a 57.3. The problem with it, of course, is it's not perfectly accurate. So if you wanted to be perfectly accurate in math, of course, what do you do instead? Well, you go to where they are, in fact, equal, which is at 180 degrees. And how many radians are in 180 degrees? Pi. That's why you're using that particular ratio right there. That being said, just as a heads up, 180 divided by pi approximates out to 57.3. So if you're in my class, please feel free, because it's faster, it's easier, and gives you a better understanding to use this guy right here. We need a good amount of decimals, so humor me real quick. For 3 degrees, what does that mean in radians? 0. What? 0.052 is fine. Okay, we'll go 3 decimals is fine. Okay, now for this next part, apologies, you do need to be in radians on the calculator because we are going to be using trig. So go ahead and take sine of that exact number as long as you're in radians on your calculator and tell me what you get.
0.05. That's what I got.
So basically at 3 degrees, they are the same. And if you go down the decimals, they're not. And I'll talk more about that. Okay, so let's skip ahead here. Let's go to 8 degrees. Do 8 degrees here. What's the angle on that? Oh, sorry, the one you just said. Give me 3 decimals. 140. Cool. And then what's the sine theta of that?
0.989.
No.
No? Bro.
0.140.
I did sign up that.
140 is correct.
Yeah, I am in
Now, you will notice already, if you're doing it along with me, which is why please be doing it along with me, okay, you might notice that those are actually not exactly the same. You had to round this to 0.14, which they're getting further away, which you can see visually with what I did over here just a second ago. They are going to get further and further away from each other. So, what if, last one I promised, 15 degrees? What is that in radians? 0.262,
I got this
and then the sine of that is
0.2.
No, just stop.
5.9.
5.9 is correct, yeah. And if you find the percent difference between those two particular numbers, what you're going to find is it's off by 1.14%. The other day on the lab, you might have saw a thing called the small angle theorem. This is the small angle theorem, that for angles, basically, the approximation is usually 15 degrees. They say it is simple harmonic motion, but here's the weird conversation that you got to kind of understand about physics in general versus like reality and that type of thing. Is it? Is it perfectly simple harmonic? No, but it's like that's off by like 1%, so it's off. It's like 99% simple harmonic, so it's not simple. But is it? Well, from this point forward, I'm going to say yes. And even beyond that, you go like, okay, so is 15 the break? Is it not simple harmonic motion beyond 15? Well, let's be clear, because it wasn't simple harmonic motion at 15. It was just 99% accurate. So I made a thing a few years back. It's basically what we just did, but a lot faster because obviously it's hard to do all those numbers quickly, as you can all see. Let's go here, chapter 10, in class. Please stick with me. I know it's the end of the day. Love you guys to death. Sometimes we gotta fight, but I'm fighting up here for you. I need you to stick with me here. Okay, so here it is. I made basically what you just did. Here's the numbers in degrees, here's the number in radians, and here's the sine theta, and over here is the percent difference, like you just calculated. Okay, here's 2.62, here's 2.59, it's off by 1.15 degrees. So let's say you're a super nerd, and you come out to me and I'm pushing a kid on the playground over the summer, and you're like, is that simple harmonic motion? I'm like, shut up, I'm off the clock, but let's pretend that I'm not right now. So I'm out at 30 degrees. You're out at 30 degrees, is that simple harmonic? Well, no, but technically neither is 15, and what you get over here is at 30 degrees, the difference is about 4.7%. So is it simple harmonic motion? I'm going to tell you yes. I mean, it's within 95% simple harmonic motion. Is my eyes or your eyes probably going to be able to notice the difference between that? No. Even out at 45, over here, and you can see the graph right here, out at 45. Okay, so it's a sizable space. If I go out to like 45, you get to see that the difference is something around like 11%. It's still 90% simple harmonic. Like if a kid's swinging back and forth, by the way, this is angle, of course, from 0, so they're not past this point over here. Okay, is it simple harmonic motion? No, but technically a pendulum never is. It's a weird conversation that you start to get into in physics where it's like, is it a thing, isn't it a thing? You've got to be smarter than that. You have to be smarter than there's a yes or no answer to these things. You have to like, is it? Well, it depends on how accurate you want to be, right? If you need to be accurate down to like the 3rd or 4th decimal, then no, it's definitely not simple harmonic motion. Okay, if you need to be accurate to like, I don't know, the 1st decimal, yeah, it's just fine. It kicks around. It describes, is a pendulum vastly more accurate in simple harmonic motion than this? Yes. Is it more accurate than this? Yes, quite a bit actually more accurate than this. You didn't know any difference. It's without a slow motion camera, but yeah, basically it's that right there. And if I go back up, you'll notice this graph, which is basically the exact same thing. It's just zoomed in on 0 to 30 degrees, right? if I gave you those blue dots and I erased all the orange ones, the blue dots are in fact the linear one. You can see that from right down here, okay? And I asked, is that a linear function? My guess is all of you guys are like, well, as far as I know, yeah, it's a linear function. And then if I erased the blue dots and gave you the orange dots and I said, is that a linear function? You'd probably say, without knowing anything else, yes, it's definitely a linear function. Is it actually? No, but for our purposes in here, beyond this point, is a pendulum going to be in simple harmonic motion? Yes. Okay, moving on.
Understand why.
Hey, I understand why though, Spain hour. And I get that it's not actually, but it could.
I'm not going to rant. I will say this.
Yeah.
Those comments.
Yeah.
Those comments. If you're saying those comments in your head, if you're joking right now and you're just messing with me, cool. If you were saying those conversations in your head, love you to death, physics is not for you. Okay? Okay? Please don't stick around. Okay? You are going to be successful in life. I have no problems with you whatsoever. But this is not for you. This is not for you.
Yeah.
I heard a phrase the other day that's kind of deep, but it's harder to think about yourself. Not everybody deserves to be enlightened.
Yeah.
And that's easy to say about somebody else. It's harder to say about yourself. Okay? And I don't think it's so different in so many different fields. I don't deserve to be enlightened in certain areas of poetry or how you work on cars or how you work on stuff. And some of you don't deserve to be in physics. Okay? Love you to death. The human mind is capable of so many different things. Okay? But walk away and then let the rest of us deal with it. Okay? All right. And, yeah, all right, moving on. All right. Last piece of the puzzle is this right here. The other day in the lab, you found this. What affects the mass spring system? I wrote one of them on the board. Mass. As mass goes up, what happens to period? You learned this in the lab.
It
Goes up. Cool. Okay, what's the other thing that affects the mass spring system? What's that? K. As K goes up, what happens to period? Goes down. Correct. And if I asked you to write just the most generic equation that could possibly be true, what would you say? Well, if mass goes up, period goes up, where should it be in the equation? On the top. Okay. And as period goes up, as K goes up, period goes down, where should it be in the equation? Now let's say I said, all right, I'm going to give you guys $100. I don't have that kind of cash. I'm going to give you $100 if you could be more accurate. What are you going to do differently about yesterday's lab?
Content friction.
Don't worry about that. Just straight up yesterday's lab, what would you do differently? And as a matter of fact, we're not going to worry about all the factors. Let's just focus in on mass and period right now. What are you going to do differently? Just to hint some of that what you need to do is up on the board. What's that? Yes, you're going to make K constant. More data. More data. And then you get more data. There it is. I've got more data for you. I got more periods. By the way, these are perfect data. This is not actually from a lab, just as a heads up. And now you've got this data. You're sitting there with this data, and you actually want to figure out if this is the equation. According to this equation that I put on the board, there's a linear relationship between period and mass. I know that one goes up, the other goes up, so this is a good starting point, but what do I do?
Was the amplitude not supposed to change?
No, it doesn't. It's weird. We'll talk more about that on Monday.
On ours.
It didn't.
He's like,
And if it did, either physics is broke or you are. Moving on. All right. Yeah, I know. This is a probability thing. All right, so what am I going to do?
What are you gonna do?
If you wanted to learn the actual mathematical relationship is
Okay,
your
yes.
hyperbolic square root, and what are you going to do?
Graph it.
Graph it. Cool. What do you want on the y?
I want.
The thing that's staying the most consistent throughout our entire lab was period. Correct. So let's make that our y.
Okay.
So I'm going to graph it. I'm going to insert a graph. I'm going to go here. I'm going to go there. I'm going to go there. By the way, this is mostly for physics 2 people, but pay attention. Here we go. And I set data. And on my data, I'm going to say that what should my x be again? Mass. Cool. There we go. What do you want for my y then again? Remind me? Period. And you graph it, and you get this relationship right here.
Wow, that looks like kind of.
That looks almost linear.
Bro, that's not.
Agree to disagree.
That's not hyperbole.
It's not a hyperbole. That is a square root function if ever it looked like one. But let's say you thought it was a linear function. Well, if you thought it was a linear function, all you would do on lab, by the way, this is a little bit different than how we've tackled this in the past. In the past, you've known what to expect out of the equation, and you just kind of like confirmed it. Now it's like, what the heck if you have no idea? Well, we're just straight up guessing. So you come on here and you develop a trend line, and with that trend line, you then just like, let's assume it's linear. Let's check how accurate linear is. Make an equation. It's not quite linear. You can see it's definitely going over here, and that's not quite it. So what would I do? I'd make a guess. And what would I probably guess this is? I'd probably guess it's a square root function. And if it was a square root function, what would you graph instead? You graph the square root of
And then
mass. Some thoughts are meant to be kept to ourselves. All right, here we go. Then, yeah, I don't care. At this point in time,
It's like I'm done.
getting whiny over Spain. We're making a graph which you have no part in making whatsoever. I think I'm going to leave that part alone. All right, here we go. So the x values. Pull this over here. We get?
That's a line.
That's a freaking line if ever I saw one, which of course tells me that that's not the equation, and what do I need to do?
Oh, it's gonna be m squared.
And then I can do the same thing with k values. I could take, what would you probably guess you'd start with them? I'll just tell you what the results end up being. If I was to take the k value stuff, what would you have me do?
I would graph it.
You graph it, and it would get probably a hyperbolic or pretty close, but to check it, what would you get? You'd probably graph what in order to get this? Probably period versus what over here? 1 over k. And then when you graph 1 over k, you get a weird thing. Instead of period versus 1 over k getting you a straight line, you actually get this shape again. Which tells me it's not entire. Hyperbolic was along the right line, but then I'm just going to continue and square root further. And I do in fact get a straight line telling me that this is also square rooted.
Alrighty.
And this ends up as the square root of mass over k. And then if you continued on this and found the slope, what you would find with the slope is a really weird result. The going right here is actually too high. This is the equation that you would use to calculate the period of a mass spring system. And I'm just going to skip the whole rigmarole with the pendulum because you only found one of them. What was the thing on the pendulum that affected it? By the way, were you talking amplitude on pendulum or amplitude on mass spring? Okay, because on pendulum, you can chalk out the simple harmonic, the small angle theorem, but you can't on mass spring. So, no, it shouldn't affect it. But length affects it, and as length affects it, what happens to period? So increase, increase, decrease, decrease is fine. Okay, so that means I should put it where?
Top.
Top. Correct. And I'll just give you the rest. Weirdly, the thing that goes down here is in fact G. Gravity does in fact affect the pendulum. And there's the whole equation for the pendulum. And if you are paying really close attention, that might trigger the fact that you've already used that equation once on what at Six Flags? Joker, which when the engine is not on is a pendulum, meaning the Joker does in fact run in simple harmonic motion, which you could have checked by measuring the time of a small oscillation of the Joker and a large oscillation there, finding probably what about a small and a large oscillation. They should be about the exact same thing, which is weird. So let's talk. That's the last thing I got for you today. You can put your stuff away as long as you're paying attention. Okay? Because if you guys remain, listen, I love you guys to death, but I think if you're going to be honest with yourselves, and if I could be honest with you, some of you have gotten like next level bitchy on me, okay? I'm trying to push pretty hard in here, and some of us have gotten like it's weird that Sprano was doing physics. No, it's not. That's what this does. So I'm just going to push back if that's the case on some of you. And if that hurts your feelings, then stop doing it to me, damn it. All right, moving on. Okay? I don't like it when it's bitchy at us. One of us started it. Love you guys. I mean that. I really do. So that's why it pisses me off when we're bitchy. All right, so let's talk about the amplitude and why it doesn't affect it. If I was running a race against my kid, or if any of you were running against a race against my kid, my guess is you would win, yes? No. Let's pretend you're twice as fast. You get there with half the time. Let's make the race fair. So you go twice the distance. If you go twice the distance, twice as fast, what should be the result of the race?
It should be a draw.
Should be a draw, correct. So in a pendulum, if I pull it back a certain distance, is there a force pushing it this way? Will that cause an acceleration? Will that cause a change in speed?
Yes.
Cool. So if I double that displacement, according to simple harmonic, what should that do to force? Double it. Which does what to acceleration?
Double it.
Which does what to your overall speed? So you're going twice as fast if you doubled the displacement, but you doubled the displacement, so what have you done to the race? you've made it twice as far. So the weirdest freaking thing, and again, if you don't believe me, then just try it if you're ever pushing somebody on the playground, is this right here at the tiniest of oscillations right over here. Like I'm barely gonna move it. If I time that, and I time that, what am I going to find? It's exactly the same amount of time. Not exactly, it's actually off by about 1%. This is a small angle here, I'm going to shut up about that. Okay, so if this is 5 times as far, then the force is 5 times bigger, but that means the acceleration is 5 times bigger, which means, of course, the velocity is 5 times bigger, but it's 5 times as far, so the race is a tie, regardless of how far it actually should be, because of the two conditions we started off with simple harmonic. Because force is proportional to displacement, that's the only reason that works. Which is also why this is not simple harmonic, and why if I do tiny oscillations, I can do them much faster than I can do big oscillations, because that's not simple harmonic. I'm not upping the force because of the displacement. I'm done.
My job.
If I hurt any of you guys' feelings, please let me know. I will apologize directly to your face. I don't intend to hurt your feelings unless it's accurate, in which case I do hope that you actually come to a realization of yourself.
Oh, you're just in the market.
That
Mood.
would've been
Oh, you missed it.
Spain arms.